Twin volcano eruptions are shaking the Pacific as Indonesia and Japan watch ash clouds rise into the sky. In this quiet report, the story follows what is known, what remains uncertain, and how these powerful Earth systems connect deep below the surface. Before the journey begins, please like this video and subscribe to the channel for more calm, science-based documentary updates. High above the Western Pacific, long bands of cloud move across a broad region of ocean and islands. The air remains cool in some layers and warm in others, shaped by seasonal winds and changing pressure systems that circle the planet in slow patterns. Far below, Indonesia stretches across the equator in thousands of islands, while Japan curves along the edge of the North Pacific in a long volcanic chain. Between them lies a complex region where oceanic plates move beneath continental crust, creating deep trenches and volcanic arcs over immense spans of time. In this upper region of atmosphere and distance, the eruptions themselves appear first as faint marks against cloud and sea. Satellite instruments observe the atmosphere continuously. Some instruments detect visible light reflected from cloud tops during daylight hours. Others detect heat from the surface and from warm ash rising through colder air. Weather agencies and volcanic monitoring centers study these observations closely because ash at high altitude can interfere with aircraft engines and reduce visibility across major air routes. Fine volcanic particles remain suspended in the atmosphere for many hours, and sometimes for days, depending on wind speed and particle size. Over eastern Indonesia, Mount Dakono on Halmahera Island continues a long pattern of persistent eruption activity that has lasted for many years. The volcano releases ash repeatedly through a central vent near its summit crater. Observations indicate that many eruptions at Dakono remain moderate in size, though the ash clouds often rise several thousand meters above sea level. Winds carry the ash away from the volcano in long grey plumes that stretch across surrounding islands and sea lanes. At times, the ash drifts westward. At other times, it moves east or north depending on changing atmospheric conditions. Far to the north, in southern Japan, Sakurajima rises near Kagoshima Bay. The volcano forms part of a larger volcanic system known as Aira caldera, created through massive eruptions in the distant past. Sakurajima remains one of the most active volcanoes in Japan. Frequent explosions release ash and gas from summit craters, especially from the Minamida crater area. Monitoring cameras often record dark eruption columns, rising sharply into the sky before spreading outward into the upper air. From great distance, these eruptions appear small compared with storms or large cloud systems, yet their influence spreads across important regions of travel and weather observation. Aviation agencies issue advisories whenever ash reaches flight corridors. Jet engines depend on smooth airflow and high temperatures inside turbines. Volcanic ash contains hard fragments of rock and volcanic glass formed by rapid cooling of magma. When ash enters an engine, the particles may melt inside the hot turbine section and then solidify again on cooler surfaces. This process can reduce engine performance and create serious hazards for aircraft. Meteorological satellites track ash clouds carefully because ordinary weather clouds and volcanic plumes sometimes overlap visually. Infrared sensors help distinguish volcanic ash from water vapor by measuring differences in thermal radiation. Scientists combine satellite observations with wind models to estimate how far ash may travel and at what altitude it remains concentrated. These models improve with constant updates, though uncertainties remain because eruption strength can change rapidly from hour to hour. In the atmosphere above Indonesia and Japan, ash plumes interact with moisture, sunlight, and wind. During daylight, Fine ash can scatter sunlight and create muted colors near the horizon. At sunset, suspended particles sometimes deepen red and orange tones in the sky. Closer to the eruption source, dense ash reduces visibility and dims the landscape beneath the cloud. Rain passing through volcanic plumes may carry ash downward more quickly, forming muddy deposits on roads, rooftops, and vegetation. The broad atmospheric setting around these volcanoes also reflects seasonal climate systems. Indonesia lies within a tropical region where warm seas supply large amounts of moisture to the air. Strong convection, which is the upward movement of warm air, often builds towering storm clouds near volcanic islands. Japan experiences a wider range of seasonal conditions, including humid summers and colder winter air masses moving from continental Asia. These changing patterns influence how eruption clouds spread and how long ash remains suspended. Monitoring agencies in both countries maintain networks that combine satellite data, radar observations, weather balloons, and ground reports. Pilots sometimes report visible ash layers or haze conditions at cruising altitude. Residents beneath drifting plumes may observe fine grey dust settling slowly across vehicles, roads, and crops. In some cases, local authorities advise people to remain indoors or wear protective masks when ash concentrations increase near populated areas. Despite dramatic images often associated with volcanic eruptions, most ash clouds disperse gradually in the upper atmosphere. Winds stretch the plume into thinner layers until particles settle or wash out through rainfall. The largest particles fall first, usually near the volcano itself. Much finer particles may travel hundreds or even thousands of kilometers before descending slowly through the atmosphere. At this outermost level of observation, the eruptions remain distant features within a moving atmosphere shared across oceans and nations. Satellite images show pale spirals of weather systems, broad expanses of sea, and narrow columns of volcanic ash extending upward into shifting winds. The activity at Dukono and Sakurajima becomes part of a larger planetary system of air circulation, sunlight, moisture, and suspended mineral dust. The atmosphere carries evidence of volcanic unrest far beyond the mountains where the eruptions begin, spreading traces of deep geological processes into the open sky above the Pacific region. Around the volcanic islands of Indonesia and Japan, weather forms the next broad layer of the setting. Air does not move as a single sheet. It moves in stacked levels, each with its own temperature, moisture, direction, and speed. Near the sea, wind may drift gently across warm water. Higher above, another stream of air may move faster and in another direction. This layered structure guides ash from an eruption after it leaves the crater and reaches the open atmosphere. The volcano supplies the particles and heat, while the weather decides much of their path. Over the Indonesian archipelago, warm ocean water feeds moisture into the lower atmosphere. The air above the sea becomes humid, meaning it carries a large amount of water vapor. During the day, sunlight warms land and water, and warm air rises from slopes, forests, fields, and coastlines. This rising air can build cloud towers in the tropical sky. When a volcanic plume rises into this moving air, ash and gas enter a setting already shaped by convection, the upward movement of warm air. The plume can rise through one wind layer, bend inside another, and spread outward when it reaches a level where the surrounding air has similar density. Near Mount Dukono, the winds around Halmahera Island shift with local terrain and broader tropical circulation. Sea breezes move inland during parts of the day as land heats more quickly than the surrounding ocean. At other times, air drains from higher ground toward the coast. These local winds affect ash near the surface, especially when fine particles descend across villages, roads, and vegetation. Above these local patterns, larger wind systems carry ash farther away, sometimes across nearby islands and sometimes out over open water. Observations from monitoring agencies show that Volcano ash plumes often move in the direction of prevailing winds at the time of eruption, which can change across days or even within a single day. In southern Japan, the weather around Sakurajima has its own layered character. Kagoshima Bay sits near steep volcanic land, coastal plains, and open sea. Wind near the bay can be shaped by mountain slopes, urban surfaces, and passing weather fronts. A weather front is a boundary between air masses with different temperature and moisture. When such a boundary crosses the region, the wind may strengthen or shift, and ash from an eruption may be carried toward different communities around the bay. In calm conditions, ash may fall closer to the volcano. In stronger winds, the plume can stretch into a long band and deposit ash unevenly across a wider area. The height of an ash plume matters because wind usually changes with altitude. A low plume remains in lower winds and tends to affect areas near the volcano. A higher plume enters stronger regional winds and may travel farther before ash settles. Volcanic ash advisories therefore describe both the position of the ash cloud and its estimated height. That height is not always exact. Satellite instruments, ground cameras, radar, and pilot reports each provide part of the picture. Observations indicate where the plume is visible. It remains uncertain how dense every part of the cloud is unless direct measurements are available. Moisture also changes the behavior of ash in the air. Water droplets can collect around ash grains and make them heavier. Rain can wash ash from the sky and bring it down more quickly. This process can clear the air but leave wet ash on surfaces below. Wet ash becomes heavier than dry ash and may cling to roofs, leaves, and roadways. In tropical Indonesia, frequent rainfall can limit how long ash remains suspended near the source. In Japan, rainfall patterns vary by season, and ash may fall through dry air or be carried down by rain depending on weather conditions at the time. Wind speed influences how concentrated an ash cloud remains. Strong winds can stretch the plume into a thinner band over distance. Weak winds may allow ash to remain more concentrated near the volcano for longer periods. Turbulence, which is irregular swirling motion in air, can mix ash upward and downward. Turbulence occurs near mountains, inside storm clouds, and along boundaries between different wind layers. For aircraft and communities, this mixing matters because ash may not remain at one neat altitude. It can spread through a thicker part of the atmosphere than a simple line on a map suggests. Temperature controls the stability of the atmosphere. Stable air resists vertical movement and may flatten a plume into a wide layer. Unstable air allows rising motion, helping a plume climb higher if eruption heat and momentum are strong enough. A plume from Sakurajima or Volcano can therefore reach different heights under different weather conditions, even when eruption energy is similar. The same volcano may produce a compact column one day and a more widely spread cloud another day because the air above it has changed. Ash transport models use weather forecasts to estimate future plume movement. These models divide the atmosphere into many layers and calculate how wind will carry particles of different sizes. Larger ash grains settle quickly. Fine ash can remain in the air longer and travel farther. The models are useful but not perfect. They depend on the starting information from the eruption, including plume height, eruption time, and particle amount. When those inputs change quickly, forecast uncertainty grows. Monitoring centers update advisories as new observations arrive, allowing the forecast to follow the real plume more closely. The weather layer also affects gases released with ash. sulfur dioxide, water vapor, carbon dioxide, and other volcanic gases enter the moving atmosphere. Some gases dilute rapidly, while others can be tracked by satellite instruments over larger distances. Sulfur dioxide can react in the atmosphere and form sulfate particles, which are tiny droplets or crystals containing sulfur compounds. In small to moderate eruptions, these effects are usually regional and short-lived. Larger eruptions can send sulfur compounds higher, where they may persist longer. For the events near Dukono and Sakurajima, observations focus mainly on local and regional air quality and aviation safety rather than global climate influence. In this weather layer, the eruptions are no longer only points on the ground. They become moving clouds shaped by winds, rain, temperature, and moisture. Ash rises, bends, thins, settles, and sometimes disappears from sight while still remaining measurable by instruments. The atmosphere turns each eruption into a changing pattern. It carries some material away, returns some material to the land, and leaves the rest as faint mineral traces moving through the sky. Below the moving weather, the island surfaces form a quieter but more immediate region of volcanic influence. Indonesia and Japan both rise from active margins of the Earth, yet their inhabited landscapes differ in shape, climate, and daily rhythm. Around Mount Dukono, Halmahera Island is covered by tropical forest, coastal settlements, narrow roads, and cultivated land. Around Sakurajima, the land meets Kagoshima Bay with communities, ports, farms, and city districts arranged around water and volcanic slopes. In this surface region, ash and official warnings become part of ordinary ground conditions. The land around Dukono belongs to North Maluku, a region of eastern Indonesia where islands are separated by channels, bays, and steep volcanic terrain. The volcano itself rises in the northern part of Halmahera. Its persistent activity means that nearby communities are familiar with ash clouds, warning notices, and restricted access near the summit. Volcanic ash may settle on leaves, roofs, wells, and footpaths. Dry ash is light and powdery, but it is not soft in a biological sense. It is made of tiny rock and glass fragments. When it gathers on surfaces, it can scratch paint, cloud windows, irritate eyes, and make roads slippery. In villages near active volcanoes, daily life often continues under careful limits. People may clean ash from water containers, cover food, protect livestock, and watch changes in wind direction. Schools, clinics, and local offices may adjust activity when ashfall becomes thicker. Emergency agencies may advise people to avoid areas within a defined radius of the crater. A radius is a distance measured outward from a central point. Such zones are not drawn because danger is equal everywhere inside them. They are practical safety boundaries based on known hazards, terrain, eruption history, and the difficulty of predicting sudden changes at close range. Around Sakurajima, the surface setting includes a long history of living beside an active volcano. Ashfall in Kagoshima is a familiar hazard, and local systems are designed around it. Roads may receive regular cleaning. Residents may use special collection bags for ash in some districts. Buildings, vehicles, fields, and public spaces can be affected by fine deposits after an eruption column drifts over inhabited areas. The volcano is close enough to urban life that monitoring information is part of regional awareness. Ferries cross the bay, roads circle the volcanic island, and observation points mark the boundary between daily movement and restricted areas. Ash on the ground changes the way surfaces behave. On dry roads, it can reduce traction and rise again as dust when vehicles pass. On wet roads, it can form a slick paste. On roofs, it adds weight, especially when rain makes it heavier, on crops. Ash can coat leaves and interfere with sunlight, though thin layers may wash away. Thicker deposits can damage plants, contaminate water, or require removal by hand. The effect depends on ash thickness, grain size, chemistry, rainfall, and the sensitivity of the surface it covers. A light dusting may be an inconvenience. A heavier fall may become a public safety problem. The shoreline setting also matters. Many volcanic communities depend on harbours, fishing grounds, ferries, and coastal roads. Ashfall can reduce visibility for boat operators and affect navigation near shore. Fine ash on decks and engines can create maintenance problems. In ports, equipment exposed to ash may require cleaning because volcanic particles can be abrasive. Around Kagoshima Bay, maritime traffic exists close to Sakurajima, so changes in ash direction can affect both land and water routes. Around Halmahera, smaller coastal routes and local transport may be affected when ash reduces visibility or when advisories restrict movement near the volcano. Local air near the surface becomes important because people, animals, and plants interact directly with it. Fine ash particles can irritate the throat and lungs, especially for people with existing respiratory conditions. The risk depends on concentration, exposure time, and particle size. Public health guidance usually focuses on reducing exposure during ashfall by staying indoors when possible, sealing openings, protecting water, and using suitable masks when outdoor movement is necessary. The ash itself is not the same as ordinary dust from soil. It may contain fresh volcanic glass and minerals formed from cooling magma, which makes careful handling important during cleanup. Restricted zones around active volcanoes are surface expressions of deeper hazard knowledge. Authorities may close trails, roads, farms, or forest areas closest to the crater. Near the volcano, the surface can be affected not only by ashfall but also by falling blocks, sudden explosions, hot material, and fast-moving mixtures of gas and rock. At this surface level, the exact inner process is less visible than its boundary on maps and signs. The purpose is practical. It keeps people away from places where short warning times make evacuation difficult. In Japan, volcanic alert levels help connect scientific observation with public action. These levels may indicate restrictions near the crater, limits on mountain access, or broader evacuation concern if activity increases. In Indonesia, monitoring agencies also issue volcano status levels and recommendations, including exclusion distances. These systems are not identical, but they share a common purpose. They translate observations into instructions for communities, pilots, local authorities, and emergency workers. The surface region therefore contains both physical deposits and human response systems. The ground records eruption activity in small layers. Each ashfall leaves a trace that may be swept away, washed into drains, mixed with soil, or preserved in sheltered places, in forests. Ash settles on leaves and branches before falling to the ground with rain. In towns, it gathers along curbs, roof edges, and drainage channels. In fields, it becomes part of the upper soil after weathering. Over long periods, volcanic ash can contribute minerals to soil, though fresh ash may create short-term stress for plants and water systems. The same material can be both a hazard in the moment and part of future land formation. On the island surfaces of Indonesia and Japan, the eruptions are experienced as ash on roofs, advisories on maps, closed paths near summits, and careful movement through changing air. The land remains inhabited, organized, and monitored. Roads continue where conditions allow. Harbours function when visibility and safety remain acceptable. Fields, forests, coastlines, and towns receive the material that the atmosphere has carried downward. In this region, volcanic activity becomes tangible without yet entering the crater itself. It rests on the skin of the islands as grey dust, official boundaries, and patient adjustment to a restless earth. Above the inhabited ground and below the open sky, the volcano slopes form a more uneven region of ash, loose rock, hardened lava, channels, gullies, and forest margins. The slopes are not simply the sides of a mountain, they are records of older eruptions, weathering, erosion, and repeated rebuilding by new volcanic material. On Dukono and Sakurajima, these surfaces carry the visible marks of activity in ways that differ from ordinary hills. The ground may be steep, unstable, and layered with deposits that can shift during rain, tremors, or fresh explosions. A volcano slope often has several textures at once. Some areas are covered by solid lava from older flows, cooled into dark rock. Other areas hold loose ash, scoria, and blocks. Scoria is a light volcanic rock filled with holes made by gas bubbles. Fine ash can rest on top of these rougher deposits like grey flour on broken stone. Rain cuts channels through the loose material, moving it downslope toward valleys and lower ground. The shape of the slope therefore changes in small ways after each period of eruption and rainfall. On Mount Dukono, the upper slopes are shaped by persistent summit activity and tropical weather. Warm rain falls through forested terrain and bare volcanic surfaces. Where vegetation is thick, roots hold soil and older ash in place. Where recent deposits are fresh, loose, or hot, vegetation may be sparse or absent. The boundary between living forest and active volcanic ground can be irregular, depending on ashfall direction, past explosions, and erosion. The surface near the summit is more exposed, with less protection from plant cover and more direct contact with falling volcanic material. On Sakurajima, the slopes show the long relationship between repeated eruptions and a populated landscape. Some lower areas support orchards, roads, and settlements, while higher parts near the craters remain within restricted zones. Ashfall can collect on steep surfaces and then move downward when rain arrives. Heavy rain can turn loose volcanic material into muddy flows known as lahars. A lahar is a mixture of water and volcanic sediment that moves downslope under gravity. It can follow valleys, drainage channels, and roads if the route allows. The danger depends on rainfall intensity, available loose material, slope angle, and channel shape. The slopes also receive ballistic fragments during stronger explosive activity. Ballistic fragments are rocks thrown through the air from the vent. They may range from small stones to large blocks. Close to an active crater, such fragments can land with force and heat. Their paths are strongly affected by explosion energy, vent direction, wind only slightly for larger blocks, and the shape of the crater. This is one reason access restrictions close to the summit are important. Even when an eruption column appears moderate from a distance, the area near the crater can receive dangerous falling material with little warning. Ash deposits on slopes can be deceptively light at first. A thin layer may look harmless, especially when it settles evenly across rock and vegetation, yet on steep ground, ash can reduce friction. Dry ash may slide in small sheets. Wet ash can become heavy and mobile. Where it mixes with older loose material, it may feed small debris flows. These movements are usually local, but they matter for paths, monitoring stations, stream channels, and any people working near the volcano. The slope is the place where airborne material becomes moving ground material. Water is one of the main forces reshaping volcanic slopes after eruptions. Rain strikes ash-covered surfaces and breaks down fine layers. Some water sinks into the ground. Some flows over the surface, carrying particles into channels. In tropical settings near Dukono, frequent rainfall can quickly rework ash. In southern Japan, seasonal rains, storms, and typhoon remnants can also mobilize loose volcanic material on Sakurajima. The process does not require a new eruption at the exact moment of movement. Material deposited earlier can become hazardous later when water conditions change. Erosion exposes older layers in gullies and cut slopes. These layers may include ash beds, lava fragments, pumice, and soil horizons that formed during quieter intervals. Pumice is a very light volcanic rock with many trapped gas bubbles. In a volcanic landscape, soil often develops between eruptions and is then buried by new deposits. Over time, the slope becomes a stacked record of activity. A fresh ash layer may cover an older soil. A lava flow may protect one area from erosion while nearby loose deposits wash away. The surface pattern is therefore uneven, both in age and strength. Vegetation responds to this uneven ground. Plants may colonize older ash and lava after weathering breaks down minerals and creates conditions for roots. Fresh ash can damage leaves and bend branches, but thin layers may later mix into soil. On slopes where ashfall is frequent, plant communities may remain patchy. Forest edges can mark differences in exposure to eruptions and erosion. Around Dukono, dense tropical growth surrounds much of the volcanic terrain. But the active upper area remains more open. Around Sakurajima, managed land and natural vegetation exist alongside ash-prone slopes shaped by frequent small eruptions. Monitoring instruments placed on or near slopes must withstand ash, rain, wind, corrosion, and impact from small particles. Cameras may become clouded by ash. Solar panels may lose efficiency when covered. Sensors need maintenance because volcanic environments are harsh. Yet slope-based instruments provide important observations of surface change, shaking, gas release, and visible ash movement. Their position close to the volcano allows them to detect changes that satellites may not resolve in detail. The slopes are also pathways for sound and vibration. Explosions at the crater send pressure waves through air and seismic waves through the ground. Seismic waves are vibrations that travel through rock. Instruments on the slopes can detect these signals and help distinguish volcanic tremor from ordinary earthquakes or surface noise. Tremor often reflects movement of gas, fluid, or magma within the volcanic system. But interpretation depends on context and cannot identify every process by itself. Observations indicate patterns. It remains uncertain exactly how every movement underground connects to each surface deposit without multiple lines of evidence. At this slope level, the volcano is neither distant plume nor deep source. It is a working surface of gravity, water, heat, and loose material. Ash falls onto steep ground. Rain moves it. Rock fragments collect in hollows. Channels deepen slowly. Vegetation returns where conditions allow. Restricted zones trace the practical edge of danger on a surface that can change without ceremony. The slopes hold the fresh evidence of eruption and the older memory of many events before it, arranged in layers that descend from the crater toward the settled land below. Near the crater rim, the volcano becomes a more confined and immediate region. The surface no longer spreads gently into roads, farms, forests, and coastal ground. It narrows toward broken rock, steep inner walls, vents, and unstable edges. A crater is a hollow at or near the summit where eruptions release gas, ash, and fragments from the volcanic system below. Around Dukono and Sakurajima, the crater region is the place where visible activity begins at the surface and where hazards can change quickly over short distances. At Dukono, the active crater area has produced frequent ash emissions for many years. The summit region is rough, altered, and exposed to repeated bursts of hot gas and volcanic particles. Ash coats the ground in fresh layers, while older deposits are cut by rain and wind. The crater rim may be uneven because explosions, collapse, erosion, and accumulation all reshape it over time. Some parts may stand as firm rock. Other parts may consist of loose fragments that can shift under weight or vibration. This makes close approach dangerous even when an eruption appears moderate from far away. At Sakurajima, the main active summit area includes craters that have produced many explosive events. The Minamidek crater has been especially active in recent decades. The crater region lies above communities and bay waters, but it is separated from everyday life by monitored exclusion zones. These zones reflect the fact that hazards near a crater are different from hazards farther away. Ashfall at a distance may be managed by cleaning and protective action, but the crater rim can be exposed to sudden blasts, falling blocks, toxic gases, unstable ground, and intense heat. The crater rim is shaped by heat from below and weather from above. Rainwater enters cracks and porous deposits, then drains, evaporates, or reacts with volcanic gases and altered rock. Acidic fluids may form when gases dissolve into water. Acidic means chemically capable of reacting with minerals and corroding some materials. Over time, this can weaken rock near vents and fumaroles. A fumarole is an opening that releases volcanic gas or steam. The ground around fumaroles can look solid while being altered beneath the surface, so the rim region may contain hidden weakness. Gas is one of the most constant features near an active crater. Water vapor is usually the most abundant volcanic gas. Carbon dioxide, sulfur dioxide, hydrogen sulfide, and other gases may also escape. Near the rim, these gases may be hot, concentrated, and irritating or dangerous to breathe. Sulfur dioxide has a sharp smell and can affect the eyes and respiratory system. Carbon dioxide can collect in low areas because it is denser than ordinary air in open windy conditions. Gases dilute more quickly. In calm pockets or depressions, they may remain more concentrated. Explosive eruptions begin at vents inside or near the crater. A vent is an opening through which volcanic material reaches the surface. When gas-rich magma rises and pressure drops, gas expands and can tear magma into fragments. The result may be ash, lapilli, and larger blocks. Lapilli are volcanic fragments larger than fine ash, but smaller than large bombs or blocks. At the crater rim, these materials can be ejected with speed. Some fall back into the crater. Some land on the rim or outer slopes. The distribution depends on explosion direction, vent geometry, wind, particle size, and eruption strength. The rim also receives heat from freshly erupted material. Blocks may land while still hot. Ash may contain warm particles close to the vent. Steam can rise where rain or groundwater meets hot deposits. These signs indicate active energy exchange at the surface. Yet temperature is not always visible. A dark rock may be hot. A pale ash layer may cover hotter material below, for this reason. Scientific teams and emergency workers use instruments and establish safety procedures rather than relying only on appearance. Visibility near a crater can change rapidly. A clear view may vanish when ash, steam, or cloud moves across the rim. the ground can become difficult to read. Edges, cracks, and depressions may be hidden by fresh deposits. Wind can lift loose ash and create ground-level haze. The crater region is therefore not only hazardous because of eruptions, it is hazardous because the surface itself can obscure its own condition. A stable-looking path may cross loose material. A quiet vent may release gas. A small emission may become stronger without enough warning for a safe retreat. Monitoring at the crater rim is limited by danger, but observations from nearby instruments help define the state of activity. Cameras record plume height, color, direction, and frequency. Thermal sensors detect heat changes at vents and fresh deposits. Seismic stations measure vibrations produced by gas movement, explosions, rockfall, and magma movement. Gas sensors measure changes in the amount and type of released gas when conditions allow. No single instrument gives a complete picture. The crater is understood through combined evidence that is updated as conditions change. For both Dukono and Sakurajima, official warnings often include a recommended distance from the crater. This distance protects against hazards that can travel outward from the vent, especially ballistic fragments and sudden ash-rich explosions. The exact distance may change when monitoring agencies judge that activity has increased or decreased. Such judgments are based on observed eruption frequency, plume height, seismic signals, gas output, and previous behavior of the volcano. The boundary is a public safety tool, not a precise line between all danger and no danger. The crater rim also preserves a short-term record of eruption pulses. Fresh ash layers may cover older ones. Impact marks from falling blocks may appear on deposits near the rim. Small collapses may modify inner walls. Rain may carve channels into ash within days. Wind may move loose particles into sheltered pockets. These details show that the crater region is constantly renewed and disturbed. It is not a fixed summit feature. It is a surface in active exchange with the volcanic system below. At this inner surface boundary, the eruption is close enough to lose its distant shape. The broad ash cloud, the weather path, the island surface, and the outer slopes all lead inward to this broken ring of rock and vents. Here, gases leave the ground before mixing with wider air. Ash begins as fragments before becoming a drifting plume. Blocks fall before they become scattered hazards on the slope. The crater rim marks the visible edge of the volcano's interior activity. Where observation becomes careful, access becomes limited, and the quiet appearance of stone can coexist with continuous volcanic change. Inside the open space above the crater, the ash column forms as a rising body of hot gas, rock particles, and surrounding air. It is not a solid column, though it may look dense from a distance. It is a moving mixture shaped by heat, pressure, particle size, and wind. At the vent, eruption energy pushes material upward. As the mixture rises, it pulls in cooler air from around it. This process is called entrainment, meaning the plume draws outside air into itself as it moves. The added air changes the plume's temperature, density, and speed. At Dukono, repeated ash emissions often rise from the summit vent in pulses. Some pulses are short and relatively low. Others climb higher before bending with the wind. The ash column may appear dark near the base because it contains a larger concentration of fresh particles. Higher up, the column may become lighter and more diffuse as air mixes into it and particles spread. The color seen from the ground depends on light, moisture, ash concentration, and viewing angle. A darker plume does not always mean a larger eruption, but it can indicate a denser ash load near the vent. At Sakurajima, explosive bursts can send ash columns sharply upward from the crater area. Some columns rise quickly, then broaden at the top when upward motion slows. This broadening occurs when the plume reaches a level where its density becomes closer to the surrounding air, or where wind shear spreads it sideways. Wind shear means a change in wind speed or direction with height. The upper part of a plume may therefore lean, flatten, or stretch even while the lower part remains nearly vertical for a short time. The base of an ash column is the most energetic visible part of the plume. Hot gas expands as pressure decreases near the surface. If magma has fragmented into many particles, those particles are carried upward with the gas. Fragmentation means magma breaks into pieces because expanding gas bubbles tear it apart. The first part of the column may contain ash, lapilli, larger fragments, steam, and volcanic gases. Larger fragments fall out quickly near the crater because gravity pulls them down faster than the upward flow can carry them. Finer ash remains suspended longer and rises farther. As the column climbs, it cools. Cooling happens because the mixture expands, radiates heat, and mixes with cooler surrounding air. The plume's ability to keep rising depends on buoyancy, which is the upward force that acts when a mixture is less dense than the surrounding air. At first, eruption momentum can drive the column upward even if the mixture is dense. Higher up, buoyancy may continue the rise if the plume remains warm and light enough. If the plume cools and becomes too dense, it may lose upward motion and spread or collapse closer to the volcano. A stable ash column is one that rises and disperses without collapsing back down the slopes in a major way. Many moderate eruptions at Dukono and Sakurajima produce columns that enter the air and then drift away. Collapse becomes more concerning when dense mixtures of hot gas and particles lose upward support and move outward near the ground. In this section, the focus remains on the rising column itself, where the upward flow competes with gravity, cooling, and wind. Particle size controls much of the column's internal structure. Fine ash behaves differently from larger fragments. Fine ash can remain suspended because small particles fall slowly through air. Larger particles settle faster and may leave the column lower down. The plume therefore becomes sorted with height. Near the base, many particle sizes may be present. Higher in the column, the finest material becomes more important. This sorting is not perfect because turbulence keeps particles mixed. Turbulence creates swirls and eddies that move material upward, sideways, and sometimes downward within the plume. Water also enters the ash column in several ways. Magma contains dissolved water that becomes gas as pressure drops. Groundwater or rainwater may become steam if it contacts hot rock or fresh magma near the vent. Moist air may be drawn into the plume during entrainment. When rising air cools, water vapor can condense into droplets, making parts of the plume look whiter. A plume may therefore contain both grey, ash-rich regions and whiter, steam-rich regions. The visible boundary between ash and steam can be uncertain, especially in humid air or cloudy weather. Lightning can occur in some volcanic ash columns, though it is not guaranteed. It forms when particles collide, separate electrical charge, and create strong electric fields. This process is more common in larger or more particle-rich plumes, but smaller discharges may also occur under favourable conditions. Observations indicate that volcanic lightning can help identify energetic ash-rich eruptions. Yet its absence does not mean that ash is absent. Many ash columns rise and drift without visible lightning. The height of the ash column is one of the main measurements reported during an eruption. Plume height helps estimate where the ash will enter the wind field and how far it may travel. It can be measured by ground observers, cameras, radar, satellite instruments, or reports from aircraft. Each method has limits. Clouds may obscure the plume. Camera angles may make height estimates uncertain. Satellites may pass at intervals rather than continuously. Radar may detect some particles more clearly than others. Because of these limits, reported plume height often carries uncertainty. The edge of an ash column is not sharp. Fresh ash mixes with air, and the concentration decreases outward from the core. From far away, the plume may look like a single object. In reality, it contains regions of different density, temperature, moisture, and particle size. Some parts may be thick enough to reduce light strongly. Other parts may be thin enough to appear as haze, for aviation and air quality. This matters because visible appearance alone does not describe the full distribution of ash. The ash column is the volcano's first vertical connection between the crater and the wider atmosphere. At its base, gas and fragments leave the vent in a hot, forceful mixture. In its middle, cooling and turbulent mixing reshape the flow. Near its top, wind and buoyancy decide whether the material rises a little farther, spreads outward, or thins into layers. The column carries solid evidence of magma fragmentation upward into the sky, while gravity quietly begins separating the larger fragments from the finer dust. In this rising region, the eruption becomes a temporary structure of heat, air, and mineral particles, standing for a short time above the crater before the atmosphere takes it apart. Within and around the ash column, volcanic gases form a thinner and less visible region of the eruption. The gas cloud moves with the plume, but it is not the same as the solid ash. It includes water vapor, carbon dioxide, sulfur dioxide, hydrogen sulfide, hydrogen chloride, and smaller amounts of other compounds. Some gases are released directly from magma. Some come from heated groundwater or seawater-influenced fluids in surrounding rock, near Dukono and Sakurajima. Gas release is part of the normal active state of the volcanoes, though the mountain mixture can change with eruption strength and underground conditions. Water vapor is usually the largest part of volcanic gas. It rises as steam and may condense into pale cloud when the plume cools. This can make part of an eruption cloud look white, especially in humid air. Water vapor alone is not the main toxic concern in open air, but it affects how the plume looks and how particles behave. Droplets may form around ash grains. Ice may form at colder heights if the plume rises high enough. These changes alter the weight and settling of particles. Though the effect varies with altitude, temperature, and moisture, carbon dioxide is also common in volcanic gas. It is colorless and odorless, and it can be dangerous when it collects in low places at high concentration. In open, windy crater areas, it usually dilutes quickly, in depressions, caves, or calm hollows. It may remain closer to the ground because it is denser than ordinary air. The main risk is near the source or in enclosed spaces where ventilation is poor. For the broader plume above Dukono and Sakurajima, carbon dioxide disperses into the atmosphere and becomes difficult to separate from background air except with instruments. Sulfur dioxide is one of the most important volcanic gases for monitoring. It can be detected by ground sensors and satellites because it absorbs certain wavelengths of light. Wavelength means the distance between repeating parts of a light wave, and different gases absorb different wavelengths. Sulfur dioxide has a sharp, irritating quality and can affect the eyes, throat, and lungs. When it mixes with water in the atmosphere, it can form sulfuric acid droplets and sulfate particles. These particles may contribute to haze and can be carried away from the volcano before falling or washing out. At Dukono, persistent activity releases gas along with ash from the active vent. The gas output may vary from day to day, depending on magma supply, shallow pathways, and the openness of the conduit. When the vent remains open, gas can escape repeatedly, sometimes reducing pressure buildup and sometimes accompanying frequent ash emissions. Observations indicate continued eruptive behavior, but the exact movement of gas through cracks and magma pathways below the crater remains only partly constrained by surface measurements. At Sakurajima, gas monitoring has long been important because the volcano is active and close to populated areas. Sulfur dioxide measurements help scientists assess changes in degassing. A rise or fall in gas output may suggest changes in magma movement, pressure, or conduit conditions, but interpretation requires care. Gas may escape more easily when pathways are open. It may also become trapped temporarily when pathways are blocked. A single gas measurement does not by itself define the state of the volcano. It becomes meaningful when combined with seismic activity, ground deformation, eruption frequency, and visual observations. The gas cloud is shaped by chemical reactions after it leaves the vent. Sulfur dioxide can oxidize, meaning it combines with oxygen through atmospheric reactions and may form sulfate aerosols. Aerosols are tiny particles or droplets suspended in air. Hydrogen chloride can dissolve readily into water droplets and fall out with rain. Hydrogen sulfide can oxidize into other sulfur compounds. These reactions depend on sunlight, humidity, temperature, and the presence of other chemicals in the air. The chemical life of the gas cloud is therefore not fixed at the moment of eruption. It changes as the plume cools and mixes. Gas and ash interact closely. Ash particles provide surfaces where gases can stick or react. Some acidic compounds may coat ash grains, affecting the chemistry of ash that later falls on water supplies, vegetation, or soil. Fresh ash may therefore carry soluble salts and acids on its surface. Rain can dissolve these coatings and wash them into streams, tanks, fields, or drainage systems. The strength of this effect depends on ash amount, gas composition, rainfall, and local water conditions. In many moderate ashfall events, simple protective steps for water storage and cleaning reduce exposure. Air quality near the ground depends on gas concentration, ash concentration, wind, and topography. Sulfur dioxide can be measured in parts per million or parts per billion, though this script keeps units written in words and avoids numerical detail. At low concentrations, some people may notice irritation. At higher concentrations, exposure can be harmful, especially for people with asthma or other respiratory conditions. Authorities may advise limiting outdoor activity when volcanic air pollution increases. These advisories are based on monitoring and public health thresholds, not on the visible size of the plume alone. Some volcanic gas reaches higher levels of the atmosphere, but most gas from moderate eruptions stays in the lower atmosphere, where weather systems disperse and remove it. Large explosive eruptions can inject sulfur dioxide into the stratosphere, the stable atmospheric layer above most weather, where sulfate particles may persist and affect sunlight for months or longer. For the ongoing eruptions considered here, the principal concern is regional air quality, local exposure, an aviation-related detection of ash and gas rather than a measurable global climate effect. Observations indicate active degassing. It remains uncertain how each short-term change in gas output relates to the exact depth and motion of magma without continued monitoring. The gas cloud is difficult to see directly, yet instruments reveal its presence. Satellites may map sulfur dioxide across a region after an eruption. Ground-based instruments may measure gas passing through a beam of light. Field teams may collect samples where access is safe. These methods show that the plume is a chemical environment as well as a visible ash cloud. It carries compounds from magma into air, changes through reaction and dilution, and returns some of its material to the surface through rain and dry settling. In this gas region, the eruption becomes more subtle. The heavy blocks have already fallen near the vent, and the ash column has begun to spread. The gases move farther, thinner, and less visibly. They mark the connection between molten rock and atmosphere through chemistry rather than weight. Steam condenses and fades. Sulfur compounds react in sunlight and moisture. Carbon dioxide dilutes into moving air. The gas cloud surrounds the ash, travels with the wind, and slowly loses its concentration as the wider atmosphere receives and disperses the invisible part of the volcano's release. After the ash column rises and spreads through moving air, gravity begins the slow return of volcanic material to the ground. Falling ash forms a quieter region of the eruption, though its effect can extend across wide areas. Ash does not descend all at once. Different particles settle at different speeds depending on their size, shape, density, and the condition of the atmosphere. Coarser fragments fall quickly near the volcano. Fine particles may remain suspended for many hours before descending gradually through still air or rain. Volcanic ash is not the same as soft ash from burned wood. It consists mainly of tiny fragments of rock, volcanic glass, and minerals formed when magma breaks apart violently during eruption. Many ash particles are sharp under magnification. Their edges are produced by rapid fragmentation rather than slow erosion. This sharpness helps explain why ash can irritate the eyes, throat, and lungs, and why it can abrade machinery, paint, and moving surfaces. Near Dukono, ashfall often occurs in changing patterns because winds shift around the volcano and across Halmahera Island. One community may receive a light grey coating while another nearby receives little visible ash. Fine particles settle on leaves, roofs, roads, boats, and water containers. In humid tropical conditions, ash may quickly become damp and clump together. Rain can wash much of it from vegetation and structures, though runoff may carry the material into drains and streams. Fresh deposits often appear smooth at first, but footprints, rainfall, and flowing water soon break the surface into irregular patterns. Around Sakurajima, ashfall has become part of long-term daily adaptation. Communities near Kagoshima Bay sometimes experience repeated light ashfall from frequent eruptions. Vehicles may carry a thin grey film. Sidewalks and roadside gutters may collect dark sediment after windy periods. Public cleaning systems help remove accumulated ash from streets and drainage areas. Residents may sweep roofs, cover equipment, and reduce exposure during heavier falls. Even small eruptions can produce noticeable local ashfall if wind directs the plume toward populated districts. Particle size strongly affects the behavior of falling ash. Larger grains descend more directly and settle near the volcano. Finer particles drift farther because air resistance slows their fall. A very small particle may settle so slowly that even weak turbulence keeps it suspended. Turbulence means irregular swirling motion in the air that mixes particles vertically and sideways. Because of turbulence, ashfall is not always steady. A cloud may pass overhead without much visible deposition, followed later by a brief increase as wind conditions shift. Ash can also fall unevenly because the eruption itself changes over time. A plume may strengthen, weaken, or pulse in short intervals. One pulse may contain more coarse material, another may contain mostly fine ash and steam. Rain within or below the plume can gather particles together and bring them down more rapidly. This process is called aggregation, when fine ash grains stick together into larger clumps. Aggregated ash may fall faster than individual fine particles and create localized patches of heavier deposition. the sound of ashfall is often subdued. Fine ash settling through calm air may produce little noise at all. The quiet nature of ash deposition contrasts with the explosive energy that created it. A broad surface can gradually become coated without dramatic movement. Thin ashfall may only become visible when it accumulates along edges, darkens wet ground, or appears against lighter surfaces in low light. The change may be subtle until morning reveals altered colour and texture across the landscape. Breathing conditions depend on ash concentration and particle size. Coarser ash usually settles quickly and is less likely to remain suspended in breathable air for long periods. Finer particles can remain airborne near the surface after deposition, especially when wind or traffic lifts them again. Reworked ash may become a continuing dust source even after the eruption plume has moved away. Public health advice during ashfall often includes reducing outdoor activity, protecting stored water, and cleaning ash carefully to avoid raising additional dust. Ash affects infrastructure in practical ways. Electrical systems may experience problems if wet ash accumulates on equipment, because moisture and mineral particles can conduct electricity more readily than dry air. Water treatment systems may require additional filtering. Air intake systems in buildings and vehicles may clog more quickly. Agricultural surfaces may need cleaning or irrigation adjustment. Aircraft avoid ash clouds because the fine particles can damage engines and reduce visibility. These effects vary widely depending on ash thickness, moisture, and the duration of eruption activity. The colour of ash deposits can vary from pale grey to darker charcoal tones depending on magma composition, lighting, moisture, and particle content. Fresh ash from basaltic to andesitic volcanoes, such as many in Indonesia and Japan, often appears dark grey. Andesitic refers to magma with an intermediate silica content, producing lava and ash that are neither as fluid as basaltic magma nor as viscous as rhyolitic magma. Under sunlight, ash may reflect a dull metallic sheen because of tiny glass fragments within the deposit. Over time, ash changes after it reaches the ground. Wind redistributes fine particles. Rain compacts layers and moves sediment into channels. Chemical weathering alters minerals and volcanic glass. Plants gradually recover where deposits are thin enough to permit growth. In some volcanic regions, older ash contributes nutrients to soils after long periods of breakdown. Yet fresh ashfall remains disruptive in the short term because it covers surfaces suddenly and alters the normal exchange of air, water, and light at ground level. Scientists study ash deposits because they preserve information about eruption style, plume height, wind direction, and fragmentation processes, grain size, layer thickness, mineral content, and distribution patterns all help reconstruct what occurred during an eruption. Even a thin layer may contain clues about vent behavior and atmospheric transport. In active systems like Dukono and Sakurajima, repeated ashfall creates many overlapping layers that record changing conditions through time. In this falling region, the eruption slows visibly. Material that once rose in a hot column now descends quietly through cooler air. Fine particles drift across bays, forests, roads, rooftops, and fields before settling into stillness. Gravity completes part of the volcanic cycle by returning fragmented rock from the atmosphere to the surface. The ash no longer moves upward with explosive force, it settles grain by grain, spreading a thin mineral layer over the inhabited and natural landscapes surrounding the volcanoes. Closer to the vent, volcanic material becomes hotter, denser, and less evenly spread than falling ash. This region contains pyroclastic material, a term for fragments produced by explosive volcanic activity. The word pyroclastic means fire-broken, and it includes ash, lapilli, bombs, blocks, and mixtures of gas and rock. Some of this material rises into the ash column, some falls near the crater, some may move outward along the ground when gravity overcomes upward motion. Near active vents at Dukono and Sakurajima, pyroclastic material marks the boundary between airborne eruption and ground-hugging volcanic force. Pyroclastic fragments begin as magma or older rock torn apart by expanding gas, vent explosions, or collapse of unstable crater walls. When gas-rich magma rises, pressure decreases and bubbles expand. If the pressure change is strong enough, the magma breaks into pieces. Some pieces are tiny and become ash, others are larger and fall quickly. Blocks may be fragments of older solid rock ripped from the vent or crater wall. Bombs are pieces of molten or partly molten material thrown out while still hot enough to change shape during flight. Near the crater, the size of fragments matters greatly. Fine ash may drift away with wind, but larger material returns quickly to the slopes around the vent. The ground close to the crater can be struck repeatedly by hot stones and blocks. These impacts may form small craters in loose deposits, break older rock, and start small avalanches on steep ground. The distribution is uneven because explosions do not always eject material equally in every direction. Vent shape, crater walls, wind for smaller grains, and explosion direction all affect where fragments land. At Dukono, repeated explosive activity supplies fresh pyroclastic material around the summit area. The volcano's active vent releases ash and coarser fragments in many small to moderate events. Over time, these deposits build rough surfaces near the crater. Then rainfall and gravity move some material downslope. Fresh fragments may remain unstable because they have not yet compacted or weathered. Steep piles of loose material can shift when shaken by later explosions. Heavy rain. Or minor slope failure. At Sakurajima, explosive eruptions can send volcanic bombs and blocks beyond the crater rim, which is one reason exclusion zones are maintained around the summit area. The most dangerous fragments fall close to the crater, where there is little time for warning after an explosion begins. Some fragments may be hot enough to scorch surfaces or start small fires in dry vegetation, though moisture, ash cover, and local conditions affect that outcome. The main hazard near the vent remains impact. Heat, and the sudden arrival of material moving too fast for safe response. Pyroclastic flows are among the most severe volcanic hazards, but they require specific conditions. A pyroclastic flow is a fast-moving, ground-hugging mixture of hot gas and volcanic particles. It can form when an eruption column collapses, when part of a lava dome fails, or when dense material spills from the crater. Not every explosive eruption produces such flows. Many eruptions at Dukono and Sakurajima send ash upward and outward without generating large ground-hugging currents. Observations indicate frequent explosive activity. It remains uncertain in any individual moment whether a dense pulse will remain rising, fall back near the crater, or move outward in a limited flow unless instruments and direct observations capture the event. A pyroclastic density current is a broader term that includes flows and surges. A density current moves because it is denser than the surrounding air and follows the ground under gravity. A flow is usually more concentrated and may be strongly controlled by valleys and slopes. A surge is more dilute and turbulent, and it can sometimes move over ridges or around obstacles more easily. Both are dangerous, because they may be hot, fast, and loaded with ash and rock fragments. Their behavior depends on particle concentration, temperature, speed, terrain, and the amount of gas mixed into the moving cloud. Close to the crater, even smaller pyroclastic movements can matter. A short collapse of hot ash or spatter may move down an inner wall. Loose blocks may roll outward from fresh deposits. Small avalanches may feed ash clouds near the ground. These events may not travel far, but they demonstrate how unstable the vent area can be. The inner slopes of an active crater are repeatedly disturbed by falling fragments, heat, gas, and vibration. Stability is temporary and local rather than permanent. Heat changes the behavior of pyroclastic deposits. Fresh material can remain warm or hot after landing, especially if layers are thick enough to retain heat. Rain falling onto hot deposits may produce steam. Gas may continue to escape through pore spaces between fragments. The surface may cool before the interior does, creating a crust over hotter material below. This hidden heat can persist longer than appearance suggests for scientific teams. Direct access is therefore limited and guided by measurement, not by visual calm. The texture of pyroclastic deposits reflects how the material formed and moved. Airfall deposits tend to blanket surfaces, with thicker layers closer to the vent and finer grains farther away. Flow deposits may fill valleys, form lobes, and show mixed grain sizes because fast-moving currents carry many particle sizes together. Surge deposits may be thinner and more widely spread over irregular ground. Around frequently active volcanoes, these deposits can overlap, making the surface a complex mixture of recent and older events. Water later alters pyroclastic material, rain cools deposits, dissolves soluble chemicals, and carries fine particles into drainage channels. Loose pyroclastic sediment can become the source for lahars when mixed with enough water. This connection is important because the hazard can continue after the explosive phase has ended. Hot, dry fragments from the vent may eventually become cool, wet sediment moving down channels during storms. The same material changes role as conditions change. The study of pyroclastic material helps scientists understand eruption energy and vent processes. Grain size shows how strongly magma fragmented. Rock type reveals whether material came from fresh magma or older crater walls. Deposit thickness and distribution show direction and strength of ejection. Temperature evidence may show whether fragments were hot when they landed. These details are gathered from safe distances when possible, or from field surveys after activity allows access. In this region, the eruption is heavier and more immediate than drifting ash. The material is no longer only a fine cloud moving through wind. It is broken rock, hot fragments, dense pulses, and unstable deposits close to the vent. Gravity takes control quickly over the larger pieces. Heat remains in the fresh layers. The crater and upper slopes receive the direct weight of the explosion. Pyroclastic material shows the volcano as a place where molten rock is shattered, thrown, settled, and sometimes driven outward along the ground in concentrated movement. Beneath the ash, gas, and broken fragments, the eruption draws from molten rock that is still hot enough to move. This inner region is the realm of lava and magma. Magma is molten rock below the surface, containing crystals, dissolved gases, and liquid melt. Lava is the same material after it reaches the surface. The change in name marks a change in setting rather than a completely different substance. Inside the volcano, magma rises through pressure and buoyancy. At the surface, lava cools, loses gas and begins to become rock. In volcanoes like Dukono and Sakurajima, the magma is commonly linked to subduction zone settings, where one tectonic plate sinks beneath another and helps generate melt at depth. By the time magma reaches shallow levels, it may have changed through cooling, crystallization, mixing, and gas loss. The exact composition can vary between eruptions and between volcanoes. Many eruptions in these arcs involve basaltic and andesitic magma types. Basaltic magma is generally hotter and more fluid. Andesitic magma is usually cooler and more viscous, meaning it resists flow more strongly. Viscosity shapes eruption style. Low viscosity magma allows gas bubbles to rise and escape more easily. High viscosity magma traps gas more effectively, allowing pressure to build. When that pressure is released, the magma may fragment into ash and larger particles. Sakurajima's frequent explosive activity reflects a system where gas-rich magma and shallow conduit conditions often produce blasts rather than quiet lava outpouring. Dukono's persistent ash emissions also indicate continuing fragmentation and gas release from a shallow active system. Observations identify eruptive behavior at the surface. It remains uncertain exactly how magma texture and gas content change from one short eruption pulse to the next without direct sampling of the moving magma. Magma contains dissolved gases because pressure underground keeps volatile compounds within the melt. Volatile means a substance that can become gas under volcanic conditions. Water, carbon dioxide, sulfur dioxide, and other gases remain dissolved more easily at depth. As magma rises, pressure drops. Gas bubbles form and expand, much as bubbles appear when pressure is released from a sealed liquid. In magma, however, the liquid is far hotter and far more viscous, and bubble growth can tear the melt apart if gas cannot escape smoothly. Crystals within magma also affect movement. As magma cools underground, minerals begin to form. These crystals increase the internal resistance of the mixture. A magma with many crystals may behave more like a thick suspension than a simple liquid. Crystals can also record the history of the magma, including changes in temperature, pressure, and chemistry. When ash or lava is later sampled, scientists can study mineral grains to understand processes that occurred before eruption. The rocks become a record of conditions that were hidden inside the volcano. At the surface, lava loses heat rapidly compared with magma underground. Air, rain, and contact with older rock cool its outer layer. A dark crust may form while the interior remains hot and able to move. If the lava is fluid, it may flow downslope in channels or sheets. If it is viscous, it may pile up near the vent or form a dome. A lava dome is a mound of thick lava that grows slowly near a vent. Dome growth can be dangerous if unstable parts collapse and generate pyroclastic flows. The present focus remains on the material itself, hot melt changing into solid rock as it releases gas and heat. The color of fresh lava depends on temperature and light. Very hot lava can glow orange or red in darkness because it emits visible light from heat. As it cools, the glow fades and the surface becomes black, grey, or reddish, depending on oxidation and mineral content. Oxidation occurs when minerals react with oxygen, often producing reddish iron-bearing surfaces. In daylight, even hot lava may appear darker than expected unless the interior is exposed. Heat cameras can reveal warm material that ordinary sight does not show clearly. At Dukono, visible lava flows are not the main feature of many reported eruptions. The activity is more often described through ash emissions from the summit crater. This does not mean magma is absent. It means the surface expression is dominated by fragmentation and gas-rich eruption rather than broad lava flow. Magma may remain within the conduit, repeatedly supplying ash and gas without producing large visible lava fields. The relationship between magma supply and visible activity is complex because a small change in pressure, gas escape, or vent blockage can alter the eruption style. At Sakurajima, lava has played a major role in the volcano's history, including earlier flows that change the island's connection to surrounding land. In current frequent activity, explosions and ash emissions are common features. The magma system beneath the summit supplies heat, gas, and melt to the active craters. Surface lava may appear during some volcanic episodes, but explosive release remains a defining part of the volcano's modern behavior. The material rising inside the system can therefore produce either flowing lava, fragmented ash, or both, depending on its state and pathway. The boundary between lava and pyroclastic material can be close. A piece of molten magma thrown from the vent may cool in flight and land as a bomb. A thick lava dome may crumble into hot blocks and ash. A lava flow may break at its front and create loose fragments. The same original magma can become smooth rock, broken rubble, ash, or dense blocks through different paths of cooling and movement. This makes volcanic deposits diverse even when they come from related melt. Cooling transforms lava into igneous rock. Igneous means formed from molten material. Fast cooling near the surface can produce small crystals or glassy textures because atoms have little time to arrange into large minerals. Slower cooling underground allows larger crystals to grow. Volcanic rocks at the surface often preserve bubbles, flow bands, fractures, and mineral grains that reflect the final moments of cooling and gas escape. These textures help scientists connect surface deposits to processes inside the volcano. Heat moves outward from magma into surrounding rock and fluids. It can alter minerals, drive steam circulation, and weaken parts of the volcanic structure. Gas bubbles rise through melt, cracks open and close, crystals grow, and pressure changes. All of this occurs before the visible eruption becomes ash, gas, or lava. The surface event is only the outward expression of a deeper thermal and chemical system. In this lava and magma region, the eruption becomes a question of molten material changing state. Magma rises while holding gas under pressure. It cools, crystallizes, thickens, and releases volatile compounds. Some of it fragments into ash. Some may reach the surface as lava and slowly become rock. The active vents of Dukono and Sakurajima show different surface details. Yet both depend on the same basic process of hot melt moving upward through a volcanic system and losing the conditions that kept it hidden below the ground. Below the zone where magma becomes lava or fragments into ash, the conduit system forms a narrow and hidden region inside the volcano. A conduit is a pathway that carries magma, gas, and sometimes broken rock upward toward the vent. It may be a single pipe-like passage in simplified drawings, but real volcanic conduits are usually more complex. They can widen, narrow, split, seal, reopen, and change through time. Their walls are made of older volcanic rock that has been heated, cracked, altered by fluids and shaken by repeated eruptions. In an active volcano, the conduit is the connection between deeper magma storage and the surface crater. It controls how easily gas escapes and how quickly magma can rise. When the pathway is open, gases may pass upward more steadily, and ash emissions may occur in frequent pulses. When the pathway becomes partly blocked by cooled magma, collapsed wall rock, or dense crystal-rich material, pressure may build beneath the blockage. If pressure then exceeds the strength of the obstruction, an explosion may clear part of the conduit and send ash, gas, and fragments into the crater. At Dukono, persistent activity suggests that the shallow pathway remains open enough to release gas and ash repeatedly. This does not mean the conduit is simple or stable. It may contain zones of cooling magma, loose fragments, hot gas pockets, and changing cracks. The repeated ash plumes indicate that material can still reach the surface. Observations show ongoing surface release. It remains uncertain how the exact shape of the conduit changes from day to day because the passage cannot be seen directly. At Sakurajima, frequent explosive eruptions show a system where shallow conduit pressure and gas movement remain active. The conduit beneath the summit craters may receive new magma from below, release gases upward, and experience temporary sealing near the top. Small changes in magma ascent, gas pressure, or wall collapse can alter the timing and strength of explosions. Monitoring records surface explosions, ground vibration, and gas release. But the conduit itself remains inferred from signals rather than directly observed. Gas movement inside the conduit is central to eruption behavior. As magma rises, bubbles grow because pressure decreases. If bubbles connect with one another, gas may escape upward through the magma and along cracks. If bubbles remain trapped, pressure increases inside the melt. This difference can decide whether activity is gentle degassing, steady ash emission, or explosive fragmentation. The conduit acts like a changing filter between deep pressure and surface release. The walls of the conduit are not passive. Hot magma transfers heat into surrounding rock. Gases and fluids react with minerals, weakening some zones and sealing others with new mineral deposits. Pieces of wall rock may break off and fall into the rising magma. These fragments can later be ejected as blocks or mixed into ash. The shape of the conduit may therefore evolve during an eruption sequence. A narrow throat may widen after explosions remove material. Another section may narrow when cooling magma sticks to the walls. Friction also matters inside the conduit. Viscous magma does not slide upward without resistance. It drags against the walls and may deform internally as it rises. Crystal-rich magma can move unevenly, with some parts flowing while others resist. Gas bubbles may collect in zones where pressure changes or where the conduit geometry slows movement. These internal variations can produce pulses of activity at the surface. A plume that appears as a series of bursts may reflect uneven gas release or magma movement within the conduit. Seismic signals give indirect evidence of conduit processes. When rock cracks, magma moves, gas pulses, or explosions occur, vibrations travel through the volcano. Some signals are sharp and brief. Others are more continuous and are called volcanic tremor. Tremor can indicate sustained movement of fluid or gas, though its exact source may be difficult to identify without other observations. At active volcanoes, scientists compare tremor with plume activity, gas output, and deformation to understand whether the conduit is becoming more pressurized or more open. Ground deformation also provides clues. Deformation means a change in the shape of the ground. If magma or gas pressure increases below the surface, parts of the volcano may swell slightly. If pressure decreases after an eruption, the ground may subside. These movements can be small, measured by sensitive instruments rather than sight. Around Sakurajima, deformation studies have long helped scientists examine the relationship between shallow activity and deeper magma supply. Around Dukono, available monitoring also supports assessment of ongoing unrest, though dense tropical terrain and access limits can make direct observations more difficult. Temperature inside the conduit remains high, but it is not uniform. Fresh magma is hottest where it rises from below. Near the upper conduit, cooling can form crusts, plugs, or hardened margins. Gas moving through cracks can transport heat upward. Rainwater and groundwater near the surface may cool outer zones and create steam when they contact hot rock. This mixing of hot and cooler conditions can contribute to pressure changes and alteration near the vent. The conduit is therefore both a pathway and a place of active physical and chemical change. The conduit may also contain fragmented material from previous explosions. Ash, lapilli, and blocks can fall back into the vent and be recycled in later eruptions. Recycled material may be reheated, broken again, and mixed with fresh magma fragments. This means not every piece ejected from a crater necessarily comes from newly rising magma at that exact moment. Some material may be older rock or earlier deposit remobilized by a later burst. Careful laboratory analysis is needed to distinguish fresh juvenile material from older fragments. Juvenile material means volcanic material formed directly from new magma. Pressure changes in the conduit can occur quickly. Gas may accumulate beneath a blockage, then escape suddenly. Magma may rise in pulses rather than as a steady stream. Cracks may open briefly and close again. These changes explain why crater regions can shift from quiet degassing to explosive release without long visible warning. Monitoring can identify patterns that often precede changes, but it cannot remove all uncertainty from a complex hidden pathway. The conduit system stands between the surface vent and deeper magma body as a narrow, changing interior corridor. It carries molten rock upward, allows gas to separate and escape, and sometimes blocks the same movement it must transmit. Its walls break, seal, heat, and alter. Its contents move in pulses of melt, bubbles, crystals, and fragments. At Dukono and Sakurajima, the visible eruptions above the crater depend on these unseen passageways below, where pressure, resistance, gas, and heat are gathered into the final route toward the open air. Around the conduit, the shallow crust forms a wider hidden region of cracked rock, stored heat, stress, and small movements. This crust is the upper part of the earth beneath the volcano, where solid rock supports the mountain while also being cut by pathways for gas, fluids, and magma. It may seem firm from the surface, but at volcanic centers it is not still. It bends slightly, breaks in small fractures, transmits earthquakes, stores hot fluids, and responds to pressure from below. The shallow crust beneath an active volcano is not uniform. Some zones are dense and strong, others are weakened by heat, water, and chemical alteration. Older lava flows, ash deposits, intrusions, and collapsed material may all be buried within it. Intrusions are bodies of magma that enter surrounding rock and cool underground, without erupting at the surface. Over time, repeated intrusion and eruption create a complicated structure. The volcano becomes an internal stack of old conduits, cooled dikes, broken rock, and altered zones. A dike is a sheet-like intrusion that cuts across existing rock. Dikes matter because magma often moves through them when it travels sideways or upward through the crust. They can open cracks as they push into solid rock. This creates earthquakes and deformation at the surface. Not every dike reaches the crater. Some stall and cool underground. Others connect with older pathways or feed eruptions. In places like Indonesia and Japan, dike movement is one part of how volcanic systems adjust to new magma supply. Beneath Dukono, the shallow crust supports a long-lived open vent system. Frequent ash emissions suggest that pathways between magma and surface have remained active over many years. Still, the surrounding crust must absorb constant stress from heat, gas, shaking, and fluid movement. Small earthquakes may occur as cracks open, rock shifts, or pressure changes. In tropical settings, groundwater and rainwater can circulate through fractures, carrying heat and dissolved minerals through the upper volcanic structure. This circulation can weaken some rocks while sealing others with mineral deposits. Beneath Sakurajima, The shallow crust lies within the broader Era caldera system. A caldera is a large volcanic depression formed after major magma withdrawal and collapse. Sakurajima's active cones rise along the southern part of this larger system. The shallow crust here records not only present eruptions, but also the structure left by older large eruptions and later magma movement. Ground deformation around the region helps scientists track pressure changes in the volcanic system. These changes may occur beneath the active cone and also within the larger caldera area. Earthquakes are important signals from the shallow crust. Volcanic earthquakes can form when brittle rock breaks under stress. They can also result from fluid pressure moving through cracks. Some are too small to be felt by people, but are recorded by sensitive instruments. Their depth, location, frequency, and waveform help scientists infer where pressure is changing. A waveform is the shape of a recorded vibration over time. Different waveforms can suggest different processes, though interpretation requires comparison with other data. Shallow earthquakes do not always mean that an eruption is imminent. Active volcanoes can produce many small earthquakes during ordinary unrest. A sudden increase, a migration of earthquake locations, or a change in signal type may be more meaningful than a single event. Observations indicate that seismic activity reflects movement and stress within volcanic systems. It remains uncertain how each small earthquake connects to a specific hidden crack without detailed imaging and long-term records. Rock in the shallow crust can deform without breaking. Pressure from magma or gas may cause the surface to inflate slightly. When pressure decreases, the surface may deflate. Instruments such as tilt meters and satellite radar can detect these subtle shape changes. A tilt meter measures tiny changes in ground angle. Satellite radar can compare repeated images of the same surface to measure movement over time. These methods reveal that volcanic ground is not perfectly rigid. It breathes slowly with pressure, though the motion is measured in small changes rather than visible swelling. Hydrothermal systems are another part of the shallow crust. Hydrothermal means involving hot water. Rainwater and groundwater seep downward through cracks, heat near hot rock or magma, and rise again with dissolved minerals and gases. This circulation can produce steam, hot springs, fumaroles, and altered rock near the surface. It can also create pressure if water becomes trapped and heated. In some volcanoes, steam-driven explosions occur when pressure builds in a hydrothermal zone. Such explosions do not require new magma to reach the surface, though they still depend on volcanic heat. The shallow crust can also store gas separately from molten rock. Gas may move through fractures ahead of magma, or escape from deeper sources into porous zones. If gas pathways remain open, pressure may release steadily. If pathways become sealed by minerals, cooled magma, or collapsed material, pressure may increase. This balance between open and closed pathways influences eruption style. At the surface, the result may appear as changing gas emissions, ash bursts, or quiet intervals. Inside the shallow crust, the process is a shifting network of cracks and seals. Temperature changes mineral strength. Hot rock can deform more easily than cold rock, but near the surface many volcanic rocks remain brittle enough to break. Chemical alteration by acidic fluids can transform minerals into clays, sulfates, and other softer materials. Altered zones may be weaker and more prone to collapse, especially on steep slopes or crater walls. This weakening is important for volcanic stability, because a strong-looking mountain can contain zones of damaged rock hidden below the surface. Scientists study the shallow crust with seismic networks, gas measurements, ground deformation, gravity surveys, magnetic observations, and geological mapping. Gravity surveys measure small differences in the pull of gravity caused by density variations underground. Magnetic observations can reveal changes in heated or altered rock because high temperature affects magnetic minerals. No method gives a complete picture on its own. Together, they build a cautious image of the hidden region around the conduit. At this shallow crust level, the volcano is a structure under strain. Solid rock surrounds moving heat. Cracks open and close. Water circulates and reacts. Small earthquakes pass through the mountain like brief messages from places that cannot be seen. The crust holds the conduit in place while also being changed by it. Beneath Dukono and Sakurajima, this region supports the visible eruptions above, storing the stresses, fluids, and fractures that guide material toward the surface through an interior that is firm, broken, heated, and slowly changing. Below the shallow cracks and heated rock, magma storage forms a deeper interior region where molten material can gather, change, and wait before rising again. This region is often called a magma reservoir, though the word does not mean a single open lake of liquid rock. In many volcanoes, storage is more like a warm, partly molten zone made of melt, crystals, gas, and surrounding solid rock. Some parts may be mobile, some parts may be nearly solid. The system can remain active even when only a fraction of it is fully molten. A magma reservoir exists because melt rising from greater depth may slow when it reaches levels where pressure, density, and rock strength change. Magma that's less dense than surrounding rock tends to rise, but it may stall when it meets a zone where upward movement becomes harder. There it can collect, cool, crystallize, mix with new magma, and release gases. This stored magma is not quiet in a simple sense. It continues to evolve chemically and physically while hidden below the volcano. Beneath Dukono, the long pattern of persistent eruption suggests continued supply from depth into a shallow to intermediate system capable of feeding repeated ash emissions. The exact size, shape, and depth of its storage region are not directly visible. Observations at the surface show ongoing release of ash and gas. Seismic and other monitoring data may indicate movement and pressure changes. It remains uncertain how much melt is stored at any given time, how much is crystal rich, and how often new magma enters from below. Beneath Sakurajima, magma storage is connected to the larger Era caldera system. Studies of ground deformation and eruption history indicate that magma supply beneath the broader caldera and active cone plays an important role in continued activity. A deep or intermediate reservoir may feed shallower pathways beneath the summit craters. Pressure changes in this storage region can appear at the surface as uplift or subsidence across parts of the volcanic area. These changes are measured carefully because they provide clues about magma accumulation and withdrawal. Inside a reservoir, magma differentiates. Differentiation means that magma changes composition as crystals form, settle, dissolve, or react with the remaining melt. Early forming minerals may remove certain elements from the liquid. New magma entering the reservoir may mix with older magma. Hotter magma may heat and remobilize cooler, crystal-rich material. These processes can produce magma with different viscosity, gas content, and eruption behavior from the original melt that entered the system. Gas behavior within storage regions is especially important. At depth, high pressure keeps many volatile compounds dissolved in melt. As magma moves upward or pressure decreases, gas begins to separate into bubbles. If gas accumulates in the upper part of a stored magma body, it can increase pressure. If cracks allow gas to escape, pressure may be released without immediate eruption. The balance between trapped gas and escaping gas helps determine whether magma remains stored, rises slowly, or contributes to explosive activity. Crystals in stored magma act like small records of time. As they grow, they preserve chemical zones that reflect changing temperature, pressure, and melt composition. Under a microscope, some crystals show rings or bands, much like growth layers in a tree, though formed by mineral growth rather than seasons. Scientists analyze these crystals in erupted ash and lava to infer conditions within the reservoir before eruption. Such studies can reveal magma mixing, heating, cooling, and movement, but they usually become available after samples are collected and examined. The storage region also exchanges heat with surrounding rock. Magma cools slowly underground because rock is a poor conductor of heat compared with metal or water. A large body of hot material can remain warm for long periods, especially if new magma continues to arrive. Heat from the reservoir drives hydrothermal circulation above it, alters minerals in nearby rock, and helps maintain weak zones where future pathways may develop. This slow heat transfer is part of what keeps a volcanic system alive between eruptions. Pressure in a reservoir is not constant. New magma entering from below can increase pressure. Gas separation can increase pressure. Cooling and crystallization can either reduce melt volume or concentrate gases in remaining liquid, depending on conditions. Eruption removes material and may reduce pressure, though deeper supply can restore it over time. These changes do not always produce simple surface patterns. A volcano may erupt while some deeper pressure remains high, or it may show deformation without immediate eruption. Magma storage is also shaped by the strength of surrounding rock. If pressure becomes high enough, rock can fracture and allow magma to move upward as a dike. If the surrounding rock is too strong, or if pressure is insufficient, magma may stall and cool. Repeated cycles of intrusion and cooling can build a complex network of solidified magma bodies around the reservoir. These solid bodies become part of the volcano's internal architecture, influencing where later magma can travel. At Dukono and Sakurajima, monitoring cannot see magma storage directly in the way a camera sees a plume. It depends on indirect evidence. Seismic waves may slow or scatter through hot, partly molten regions. Ground deformation may suggest pressure changes. Gas output may reveal that volatiles are moving from stored magma toward the surface. Erupted rock chemistry may show mixing or replenishment. Each clue is valuable, but each has limits. Scientific consensus treats magma reservoirs as dynamic zones rather than simple tanks, and uncertainty remains part of any interpretation. The deeper storage region connects short eruptions to longer cycles. A single ash plume may last minutes, while magma supply and storage may evolve over years or decades. Persistent volcanoes can release small amounts of material many times, while the larger system continues to receive, store, and adjust magma below. This long rhythm does not always appear dramatic at the surface. It may be measured in slow ground motion, gradual gas changes, or subtle shifts in the chemistry of erupted ash. In this region, the volcano becomes less like an open pipe and more like a living heat engine inside solid earth. Melt gathers among crystals, gas stays dissolved, separates, or escapes. New magma enters older material. Pressure rises and falls slowly or in pulses. Surrounding rock bends, cracks, and warms. Beneath Dukono and Sakurajima, the storage zones remain unseen, yet their state influences the activity that reaches the crater. The eruptions above are brief surface expressions of deeper reservoirs where molten rock is held, changed, and prepared for its next movement toward the surface. Below the magma storage region, the wider tectonic setting becomes the controlling structure. Indonesia and Japan both sit along active plate boundaries, where oceanic plates move beneath other plates in a process called subduction. Subduction means one tectonic plate sinks into the mantle beneath another. This movement is slow on the human scale, but it is powerful enough over geological time to build volcanic arcs, deepen ocean trenches, lift mountains, and feed magma systems. The volcanoes at the surface are local expressions of this much broader movement. Around Indonesia, several tectonic plates and smaller plate fragments meet in a complex pattern. The region includes parts of the Indo-Australian plate, Eurasian-related plates, the Philippine Sea Plate, the Pacific Plate, and smaller blocks that interact across eastern Indonesia. Halmahera, where Dukono rises, lies within one of the more complicated parts of this system. Subduction and collision have shaped the island's volcanic arc, creating pathways for magma generation beneath the crust. The details are intricate, but the main process remains the same. A descending slab carries oceanic material downward, and that descent helps create conditions for melting above it. Around Japan, the plate setting is also complex. The Pacific Plate and Philippine Sea Plate move beneath parts of the Japanese island arc, near Kyushu, where Sakurajima stands. The Philippine Sea Plate subducts beneath the edge of southwest Japan. This subduction contributes to volcanic activity across the region. Sakurajima belongs to the volcanic front associated with this plate interaction. Its activity is therefore linked not only to the cone itself, or the Aira caldera system, but also to the deeper movement of oceanic lithosphere beneath the island arc. Lithosphere means the rigid outer layer of Earth, including crust and the uppermost mantle. The descending oceanic plate is cold and dense compared with the hot mantle around it. It sinks because oceanic lithosphere becomes denser as it ages and cools. As the slab descends, it carries water-bearing minerals, sediments, altered oceanic crust, and trapped fluids downward. These materials formed or changed while the plate lay beneath the sea. Ocean water entered cracks, reacted with minerals, and became bound within the rock. Sediment from the ocean floor accumulated on top. Subduction transports this water-rich material into hotter depths. Water plays a central role in volcanic arcs. The mantle above the subducting slab is hot but often not fully molten because pressure keeps minerals stable. When water and other volatile compounds are released from the descending slab, they enter the overlying mantle wedge. The mantle wedge is the region of mantle between the sinking slab and the overriding plate. Water lowers the melting temperature of mantle rock, allowing partial melting to begin. Partial melting means only some minerals melt while others remain solid. The melt that forms is less dense than surrounding rock and can begin rising toward the crust. This process does not create magma in a simple straight line beneath every volcano. Fluids leave the slab at different depths. Melting occurs in zones rather than points. Melt may rise, stall, mix, crystallize, and change before it ever reaches a volcano. The surface position of a volcanic arc reflects the geometry of the subducting slab and the thermal structure above it. Volcanoes tend to form where the conditions for melt generation, ascent, and storage align over long periods. Earthquakes are another sign of subduction. As plates press against each other, stress accumulates along boundaries and within the descending slab. Some earthquakes occur where the plates are locked and then slip. Others occur deeper within the slab as it bends, dehydrates, or changes mineral structure. These tectonic earthquakes are part of the same plate system that feeds volcanic arcs. though a single earthquake does not automatically produce an eruption. The connection between tectonic stress and volcanic activity is complex. Observations indicate that large earthquakes can sometimes affect volcanic systems, but it remains uncertain in many cases whether a particular eruption pulse is directly triggered by a particular earthquake without detailed evidence. Subduction zones also build long chains of volcanoes. In Indonesia, volcanic arcs extend across many islands, forming one of the most active volcanic regions on Earth. In Japan, volcanic chains follow the island arc above subducting plates. The spacing of volcanoes reflects deep processes, crustal structure, magma pathways, and the history of each segment of the arc. Some volcanoes erupt frequently. Others remain quiet for long intervals. Some produce mostly lava. Others produce explosive ash-rich eruptions. These differences arise from magma composition, gas content, storage depth, crustal conditions, and local structure. The magma produced above a subduction zone often contains more water than magma from some other tectonic settings. Water-rich magma can become explosive because gas expands strongly as pressure decreases during ascent. Silica content also affects viscosity. More viscous magma holds gas more effectively, allowing pressure to build before release. This is one reason many arc volcanoes, including those in Indonesia and Japan, can produce ash columns, pyroclastic material, and explosive eruptions. The deeper subduction process does not determine every detail of an eruption, but it supplies the broad conditions that make these volcanoes active and potentially explosive. At the scale of plates, the eruptions at Dukono and Sakurajima are small surface events within a vast tectonic engine. The plates move only gradually, yet their movement supplies water, heat transfer, melting, magma ascent, and crustal stress through long spans of time. The volcanoes do not erupt because plates suddenly move in a visible way each day. They erupt because plate motion has built and maintained systems where magma can be generated, stored, and released. The subduction zone is therefore the deep regional framework beneath the islands. Oceanic crust descends. Water-bearing minerals break down. Fluids enter hot mantle. Partial melt forms and rises. Overlying crust stores, modifies, and channels that melt. At the surface, ash columns and gas clouds appear as brief signs of this hidden movement. Beneath Indonesia and Japan, the plate boundary continues its slow descent, carrying the memory of ancient seafloor into the earth and sustaining volcanic arcs along the edge of the Pacific. Beneath the descending plates and volcanic arcs, the mantle source forms the deepest region in this path. The mantle is the thick layer of earth between the crust and the core. It is solid over most of its volume, but it can flow slowly over geological time because heat and pressure allow rock to deform. This slow movement is not like liquid water moving in a stream. It is the gradual motion of hot solid rock under immense pressure, carrying heat from Earth's interior toward the surface through convection. In subduction zones beneath Indonesia and Japan, the mantle source of magma lies above the sinking slab in the mantle wedge. This region contains hot rock that can begin to melt when water and other volatile compounds arrive from the descending plate. The mantle rock is mostly solid, but partial melting creates small amounts of liquid between mineral grains. That liquid is magma at its earliest stage. It begins as a small fraction of the source rock, not as a large empty chamber. The main minerals in the upper mantle include olivine and pyroxene, with other minerals present depending on pressure, temperature, and composition. These minerals are stable under dry conditions at high pressure, but the addition of water changes their melting behavior. Water weakens chemical bonds within the minerals and lowers the temperature needed for melting. The process is called flux melting, meaning melting helped by the addition of a volatile substance. In volcanic arcs, this is one of the main ways magma begins. The descending slab does not melt completely in most ordinary arc settings. Instead, it releases fluids as minerals break down under increasing pressure and temperature. These fluids rise into the hotter mantle wedge above. The mantle then melts partly, producing magma that is usually basaltic at first. As this magma rises, it can change through crystallization, mixing, and interaction with crustal rocks. By the time it feeds volcanoes such as Dukono or Sakurajima, it may have become more complex in composition and behavior. At this deep level, no human instrument directly watches magma form in real time. Scientists infer the source process from seismic imaging, laboratory experiments, volcanic rock chemistry, heat flow, and plate motion. Seismic waves travel differently through colder slab, hotter mantle, solid rock, and partly molten zones. Laboratory studies recreate mantle pressures and temperatures to learn when minerals melt. Chemical analysis of erupted rocks reveals traces of the mantle source and the fluids that modified it. These lines of evidence support the broad model of subduction-related melting. While details of each volcano's source remain partly uncertain, the mantle source is governed by pressure as much as heat. Deeper rock is hotter, but it is also under greater pressure, which can keep it solid. Melting begins when conditions cross a boundary, where minerals can no longer remain fully solid. In mid-ocean settings, pressure drops as mantle rises, causing decompression melting. In subduction settings, water lowers the melting point and allows melt to form at depths where dry mantle would remain solid. This distinction helps explain why volcanic arcs appear above sinking plates rather than randomly across the continents and oceans. Once melt forms in tiny spaces between crystals, it begins to separate from the solid source rock. Because the melt is less dense than the surrounding mantle, it tends to rise. The earliest pathways may be microscopic films and connected pores. With enough melt, these pathways combine into larger channels and zones of movement. The ascent is slow compared with an explosion at the surface, but it is rapid compared with the movement of solid mantle. Rising melt carries heat, dissolved water, carbon, sulfur, and trace elements upward. The chemistry of the source influences the character of later eruptions. Water-rich, mantle-derived magma can carry more volatile material into the crust. Trace elements from sediments, altered oceanic crust, and slab fluids can leave chemical fingerprints in volcanic rocks. These fingerprints show that the magma is linked to subduction rather than to a dry mantle source alone. Rocks erupted from volcanic arcs often contain evidence of this mixture. Mantle melt modified by fluids and materials carried down from the seafloor. The mantle source also receives material from Earth's surface through subduction. Oceanic crust that once formed at mid-ocean ridges becomes altered by seawater, covered by sediment, and eventually carried downward at trenches. Some of its water and chemical components return upward through volcanic gases and magma. This creates a deep cycle connecting ocean water, seafloor minerals, mantle melting, volcanic eruption, atmospheric gases, and surface deposits. The cycle is slow, but it links the outer Earth to its interior. Heat within the mantle comes from several sources. Some heat remains from Earth's formation, some comes from radioactive decay of elements inside the planet, some is transferred through movement of hotter and cooler rock. This heat does not escape evenly. Plate boundaries, mantle plumes, and volcanic arcs are places where heat reaches the surface more actively. Indonesia and Japan sit along one of the most dynamic margins of this system. where the sinking of plates helps focus melting and volcanism into long arcs. At the depth of the mantle source, individual eruptions are not separate events in the way they are at the surface. The source does not respond to each ash plume as a visible pulse. It supplies melt over long intervals, and that melt passes through many stages before any eruption occurs. Storage, crystallization, gas buildup, conduit movement, and surface pressure all modify the signal from depth. The mantle begins the process, but it does not control every detail seen at the crater. Beneath Dukono and Sakurajima, the mantle source remains unseen and immense. It is a region of hot solid rock, added water, partial melting, and slow upward transfer of material. The eruptions at the surface are brief expressions of this deep system. Ash falls in minutes or hours. Gas disperses in wind. Lava cools into stone. Far below, mantle rock continues its slow motion, and small fractions of melt begin their long passage upward in this deepest region. The frightening surface image becomes part of a measured earth process, heat moving outward, plates descending inward, and molten material forming quietly within solid rock. The eruptions settle into scale. Ash has risen, drifted, fallen, and become part of the ground again. Gas has thinned into moving air. Heat has passed from molten rock into stone, water, and atmosphere. Around Indonesia and Japan, the volcanoes remain active parts of a larger Earth system, neither separate from daily life nor separate from the deep movement below the islands. Dukono continues to release ash through a long-lived open pathway, and Sakurajima continues to show the careful rhythm of a closely watched volcano near settled land. Their activity is monitored through satellites, cameras, seismic instruments, gas measurements, and reports from communities and aircraft. Observations describe what is visible and measurable. Some inner details remain uncertain because the deepest parts of a volcano cannot be seen directly. The outer sky carries the plume, the weather shapes its path, the island surface receives its dust, the slopes hold loose material, the crater releases heat and gas, the conduit carries pressure upward, the crust bends and cracks, the reservoir stores changing melt, the subduction zone supplies water and motion, the mantle source begins the slow formation of magma in solid rock. Nothing in this path needs to be hurried. The volcanoes work through pressure, temperature, gravity, and time. Their ash clouds may appear suddenly, but the processes behind them are old and steady. Rock melts, rises, breaks, cools, and returns to the surface as layers. Wind moves the lightest grains away. Rain presses them down. The landscape adjusts in small steps. In the quiet after the description, the scene becomes simple again. Islands rest under moving air. Mountains stand above bays and forests. Instruments keep watch. Deep below, heat remains. The earth continues its slow motion, carrying change through stone, water, and sky.